All right, well, welcome back. So this is a video where I just want to talk about some properties of linear functions and use these properties to kind of do one more check about whether or not something is linear. And so this says if we have a linear function, keyword being linear, then t of 0 has to be equal to 0. And one thing I do want to point out here just for a second, this is an input. So this is a 0 vector in Rn. So this 0 vector has n zeros. And this vector is an output, so it lives in Rm. So for example, you know, if our map were something like R2 to R3, then inputs are going to be, an input would be something like 0, 0, and an output would be something like 0, 0, 0. Okay. Right, so that's not important for how we're going to prove this, but it's just important to always keep track of those little things. It's always good in life to keep track of where things are. Okay. And so why is this true? Well, this is true for a pretty simple reason, right? So why? Well, t of 0 is the same as t of 0. Right, this is a scalar. And right, 0 times the 0 vector surely is equal to 0. But then by linearity, so this is by the linearity property. Linearity says anytime we have a scalar inside of our linear function, we can pull that scalar out. So I've taken that 0 and I've pulled it out. And now I've got 0 times t of 0. And I say, I don't know what this is. But I'm multiplying it by 0. And so any vector times 0 is going to be the 0 vector. Because it's just going to zero out all of those entries. And so what have I shown? I've shown that t of 0 is equal to 0, which is what we wanted to show. Okay. So what this shows is that anytime you have a linear function, that it has to send 0 to 0. And so if you have a function that does not send 0 to 0, so if you have a function that doesn't send 0 to 0, then t is automatically not linear. Right? And that's pretty cool. That's pretty cool. So let's just do like a quick example of that. Right? So I think an example we did earlier was, I guess I can call it t of x. So t from R to R that said t of x equals, I think it was 2x plus 3. Okay. Well, we can just check immediately that t of 0 is, I guess we should think of these as vectors. So t of the vector 0 is going to be the vector 3. Right? And that's, so since t of the 0 vector is not equal to 0, this is not linear. And maybe if you want to do pause the video and work through this yourself, you could do the same thing with this transformation, say from R2 to R2, given by t of xy equals x plus 1, y plus 1. Okay. So go ahead and pause the video and check to see where 0, 0, where the 0 vector goes. And you'll see that it does not go to the 0 vector, and therefore this function cannot be linear. Okay, very good. Good. And so there was one more property I wanted to go through, which is up here, and I don't want to stress it as much because I think this tends to be a little bit more intuitive, but the idea is if I have a sum of a bunch of things, like say I have a linear combination here, well, the idea of linearity says that I can transfer I can take this sum, right? Right, because it's linear, I can break this up as a sum of a bunch of different, all of these components. Let me move this over so I have more room. Right. So because of the addition property, I can break this up like that. And then because of the scalar property, I can pull each of these scalars out. Okay. And so this property will be useful sometimes. And basically what it says is if I do T of a linear combination, then my answer is equal to a linear combination of T of the V's. So I can even be a little bit more specific here. If I have a linear combination of the vectors V, Vi, so V1 through Vp here, then the output is going to be a linear combination of T of those things. Okay?